Hello, this video introduces Hooke's Law. Lots of machines over the years. We've had springs in them, like in suspension on cars or regulators and things like that. So it's important that we had a decent model. And those springs could be either being compressed or stretched. We need a model that works for both. So in the first video we're going to understand Hooke's law and how we can use it. In the second video we'll look at the energy in springs and also look at simple harmonic motion with springs. So at the same time Newton was working on his laws, Robert Hooke was working on springs in Oxford. And what he found is if he could put a mass, different weights onto a spring, and then he measured the extension of the spring over its ordinary length, natural length. He got a whole series of points here, so force along the bottom, extension sort of in meters going up, force in newtons going that way. He found he got a straight line, yeah, so he found there was a linear relationship. And we write this relationship as effectively a proportional relationship. F is proportional to x, where x is the extension. It's usually in its first version written as F equals kx. Now you'll note that the k is at this, so the x is on the right and the F is on the left. That's because it's the extension. If we take a piece of material and we extend it, we end up with a force. So that's the driving relationship between the two. Now, worth bearing in mind that one of the concepts here is that a spring has a natural length. So when it's got no force on it, it's still got a length. What then happens if we put some force onto it, it extends by a distance x, yeah? So we've got natural length L and extension x. Now you'll also see Hooke's law described in this formula here. And you'll see here that this lambda over L is actually our K value. And what we've done is look at what's making up that K, that constant. And the first part is the lambda on the top. That's a function of the material, called a modulus of elasticity. And L is the natural length of the spring. Let's just talk about why we've got those two where they are and their effects. So, first thing is material. If I take a piece of material and I extend it by 1 centimetre, yeah, if my spring was made of steel, it would take a lot of force to extend it by 1 centimetre. If it was made by rubber, it would take a lot less, and if it was from an elastic band, it would be much less. So it is important, the material we've got, and we would get a value lambda for that material and the cross-sectional area combined together. Our lambda tells us what's happening with the material, yeah. So if the lambda is increased, so say we're using steel, so we would need more force to extend it. That's the first part. Second part is length, and on present the natural length is on the bottom here, yeah. So let's have a think about why that is. So if I take a 1 metre piece of elastic, say, and I extend it by 10 centimetres, yeah, that's an extension of 10%. Whereas if I had a 2 metre spring and I extend it by 10 centimetres, I'm only having to extend that material by 5%. So in the upper one, if I got my atoms from my original material, well, they're getting moved further apart with this extension than in my lower one, where they're going to be still closer together, yeah. And that's what causes force within a material, is your atoms trying to hold themselves together. So therefore, if my material is longer for a particular extension x, I'm going to need to apply less force. So let's just work that out. If I make the length longer here and I keep the numerator the same, the lambda and the x, then my force is going to come down, isn't it? And therefore I need less force. And if I looked at that on a graph here, so if I wanted to extend by 1 centimetre, So my 2-meter section, I would need less force than I would for my 1-meter spring. Yeah. So that's why the L is on the bottom. Makes sense, because we putting less extension into the atoms and the atom's lattice. Okay, let's use that version of Hooke's law to calculate what's going to happen, the extension, if I add a 10 kilogram weight onto the bottom of this spring. I know what the parameters are for this spring. Lambda is 490 newtons and L is, the natural length is 2 meters. So substituting those in for lambda over L, I've got 490 over 2. So I've got that the force is going to be 245x. So what we're going to do next, well, we're going to add that weight, we'll let it settle down so it's in equilibrium. What's going to happen? Well, F equals ma. If we're in equilibrium, there's no acceleration. So all we need to know is that the force down must balance the force up. So 10g, that's my weight force. Gravity force must equal 245x. Therefore, x must equal the 10g divided by 245. Therefore, x, the extension must be 0.4 meters. And therefore the overall length of the spring is now the original natural length of 4 meters plus the additional 0.4. So therefore this will have extended from 4 meters. There'll be an extra 0.4 there, won't there? So the whole thing is now 4.4 meters long. Yeah, there we go. So there we have it. Hooke's law. The force from a spring. We've got 2 versions of the equation there. We've got three parameters to work with: the extension, the natural length, and the modulus of elasticity for that material. And there you go.